Take any book on the world history of numbers. For example, take Georges Ifra's The Universal History of Number. Its table of content shows a striking phenomenon. Chapter 12 deals with the Sumerians. Chapter 13 concentrates on Mesopotamia. Chapter 14 on Egypt. Chapter 15 on Crete and the Hittite kingdom. Chapter 16 on Greece and Rome. Chapter 21 on the Chinese civilization, and so on. An organization of this kind, which treats peoples, civilizations in different separate chapters as different with respect to number, does not seem surprising to us. We have got used to it. Indeed, most histories of numbers are structured in a similar way. For instance, the same remark holds true for Geneviève Guittel's Comparative History of Written Numerations. Here is the tree summarizing the argument of her book. It presents an overview of the different principles according to which numeration systems were formed. Guittel argues that any numeration system to which documents attest falls within one of the three main types she identified. Within each of these types, she highlights criteria that characterize subtypes. These are the nodes down there, and so on. So the tree divides into branches and sub-branches, and the bottom line contains the different numeration systems attested, each of them being associated with a people. To the left, Egypt 1, hieroglyphic. Then the Aztecs, Greece 1, Attic, Rome, Sumer, Egypt 3, and so on. As the caption of the diagram here makes clear, for Guittel, the tree constitutes a hierarchical classification of written numerations. That is to say that from left to right, the numerations are displayed in an order of increasing mathematical value. To the very right, you find India with the decimal place value system that we commonly use today. Decimal because we count from 1 to 10 and hundreds and thousands and so on. Place value because when we write 1, 2, 3, the 1 means 100 because it is placed at a given position. The 2 means 20 because it is placed at a given position. It is to the nature and history of this numeration system that this talk will be devoted. But before I get there, I will need to make some observations with respect to the tacit assumptions that have underlain the histories of numbers available today. To return to Guittel's tree, we thus have her historical classification of historical and hierarchical classification of numeration systems. The tree also tells how, in her view, numeration systems evolved. She expresses these processes of evolution using horizontal arrows. So, for instance, from left to right, you have an arrow linking Egypt 1 to Egypt 3. We have moved from the hieroglyphic script to the hieratic script. Another arrow links Egypt 1 to Egypt 2. We are still within the hieroglyphic script, but this arrow refers to what Gittel reads as an improvement in the numeration system. Improvement that are in one case parallel to a change of script, in another case within a given script. Whatever the case might be, you see that for Gittel, the evolutions of numeration systems all occur within peoples. Hence, this overwhelming presence of peoples and civilizations as the major actors in this history of numbers, as is shown again by the structure of Gittel's book. Here we have Egypt and Aztecs. These are the first two that are neighboring rods here. Then Greece 1 and Rome. Again, the same idea of neighboring numeration systems. In fact, there is an arrow that links Sumer here to another numeration system attributed to Babylon. The next chapter brings together Sumer and Babylon, so we have shifted from a logic of neighboring nodes to a logic of gathering scripts. And when we turn to China, it's yet another principle, since now she gathers all information with respect to numeration systems attested to in China. About this way, which is widespread, of writing the history of numbers, my question is this. Is it obvious that a structure of this kind is appropriate? Is it obvious that the history of numbers should be cut into chapters, each related with a people or a civilization? I will argue that this common feature of histories of numbers derives from a tacit assumption that has been widely adopted and needs to be reconsidered. To explain this point, I will focus on how the history of numbers in China was treated in a monograph that served as a basis of Gittel's and also of Ifra's chapters with respect to China, namely the section about mathematics published in Joseph Needham's encyclopedic book Science and Civilization in China. In the book 3, you have the monograph that Needham wrote with Wang Ling about mathematics in China. The account of numeral notations given by Needham and Wang draws on a table entitled Ancient and Medieval Chinese Numeral Signs. In this table, the authors gather together the numeral signs attested in China during the period indicated. I have highlighted parts in the table to analyze it with you. To the very left, you have in blue the characters with which one writes today the Chinese language. Because they are characters writing down number words, I translate them as number words. 1, O, and E. Okay? So you have to imagine that characters correspond to number words. It is as if instead of 1, 2, 3 that I mentioned a bit earlier, I had written O, N, E, then H, U, N, D, R, E, D, and so on. Okay? So Needham and Wang begin to the left with the characters of the Chinese language, and then begins a chronological arrangement of numerical signs. First, in the brown column, they record the numerical signs that were found on the earliest known Chinese documents, written on oracle bones, and they gather these signs in this column. Again, I translate for what they are. They are number words. This is column E, to which I will return. So the earliest extant numerical signs from China come from documents and are number words. In column H, Needham and Wang assert that between the 2nd century before the Common Era and the 4th century of the Common Era, there emerged in China a numerical system that was decimal place value. Hence, my translation, this time with 1, 10, 2, 20, 3, 30, no longer number words, but other types of numerical signs. So the system used, to which they refer, is a system in which units, there is a mistake here, units are written with vertical rods, so 1 rod, 2 rods for 2, 3 rods for 3, and so on, until here, when we have still vertical rods for units and horizontal words for 5. Then, to get to the tens, one shifts to a horizontal rod, one horizontal rod, 2, and again the same system of horizontal rods referring to tens, additional tens, and the vertical rod here referring to 50. Then when one goes to the hundreds, one goes back to the right column, to the thousands, one goes back to the left subcolumn, and so on. And what the table argues is that between this time when we have these numerical signs and the time when we have, in column H, this place value notation for numbers, we can observe a process of evolution thanks to documents that record the evolution of signs from this type of signs to that type of signs. So you see here that they put numerical forms that they found on coins, for instance. I translated each time with number words or other types of numerical signs to show you the rhetoric of this table. So what this table claims is that the numerical system, which is decimal place value, the one we use commonly today, originated in China and not in India, as is still generally assumed today. I'm not so much interested in discussing this thesis. Rather, I would like to focus on a tacit assumption underlying this table. Indeed, for Needham and Wang, all the numerical signs that are gathered, so this is the thesis which claims that the place value decimal system originated in China. So I'm going to focus on what, in my view, is a tacit assumption underlying the table. For Needham and Wang, all numerical signs that are gathered in this table have a first and common basic function. they are all used to express numbers, to express quantities. And for this first function that they share, they seem to be interchangeable. It is true that today, if I want to write that I have bought 123 chickens, I can write 1, 2, 3 chickens, or I can choose to write O-N-E, H-U-N-D-R-E-D, and so on, chicken. It is true that today, these ways of writing quantities are interchangeable. But the question is, has it always been the case? Note that if we assume that all the numerical signs that were introduced had, in the first place, the function of expressing numbers, it would not be surprising that the history of numbers be linked to the history of language and writing. And as a result, it would not be surprising that linguistic groups appear as the natural actors of the history of numbers. Is this assumption valid? I argue it is not. But I claim that this tacit assumption has been more generally central in the history of numbers that were written to this day. Take, for example, Gittel's book. I have not emphasized the title, which reads Comparative History of Written Numeration. What does she mean by written? She makes it explicit. For Gittel, a written numeration is a well-designed written numeration merely translates with conventional signs a spoken numeration. So for Gittel, numerations to be taken into account in a history of number are those corresponding to an oral numeration. Those whose basic function first is to write down language and accordingly to express numbers. I repeat, the same assumption underlies all the histories of numbers that I could read. Now we are going to have a quick look at Chinese mathematical sources to see that there is a problem with these assumptions. What I would like to establish is that for Chinese authors, those we are going to consider, rod numerals, these numerals that were written with rods, I will be more precise in a moment. For these Chinese actors, these rod numerals were not used interchangeably with the characters writing the language. To make this point, we will first focus on a 13th century late text. You will soon understand why. So this is a page taken from Qin Shao's mathematical writings in 9 chapters, published in 1247. So I have highlighted 2 types of what I will call scriptural spaces in this page. You see, even if you do not read Chinese, that in the blue columns, you have Chinese characters. So this is the text of the mathematical writing. And what you see is that in between the sentences where the language is written, you have wider spaces where you have the famous rod numerals. The key point is that the rod numerals never occur in this part of the text, in the language part of the text. This is 9 Trun, which I have translated with the number word 9. This is 9 with Trun written on top, which I have translated with are digit 9. So you see that you have two scriptural spaces on the page, and the numerical signs are never mingled. This is even clearer in this document, which is one of the earliest documents in Chinese in which the rod system appears. So if we look at this document, it's a table of multiplication. If we look at this document, we see reading from right to left, once 9 like 9. This is with characters of the Chinese language. And then this 9, which is written with a character, is repeated with the rod numerals. And you can see that in all the parts I have highlighted in red, you only have characters. And at the end of each sentence, you have the other numerical signs. Clearly, they are different, but what is the key observation is that you will never find, when you write 7 times 8, 56, 7 and 8 will never be written with the rod numerals. Okay? So we have two systems of numeration that are clearly not interchangeable. So why did I begin with writings from the 13th century, the 10th century? That's because, by contrast with what we have seen, before the 10th century, mathematical writings in Chinese only contain characters. I have highlighted here numerical values that are stated. They are written only with characters. However, the texts refer to a surface. The text refers to rods. The text refers to moving rightwards, leftwards the rods. So, first of all, here too, before the 10th century, there were two scriptural spaces. The scriptural space of the page on which you wrote, and the scriptural space on which you represented numbers with rods. Rod numerals did not write language at the time. What happens is that after the 10th century, we observe, and it's a very interesting echo with the previous talk, we observe a transfer onto paper of this system that was written with rods previously. We have early descriptions of how rods were written, how rods were used to write numbers on the surface, and we can establish that it was a similar numeration system using rods, and that this system was illustrated onto paper after the 10th century. There is a strong continuity between the system that was written materially and the system that featured on paper from the 10th century onwards. Interestingly enough, if we return to Gittel's tree, you have China here for the type, which is the type of numeration that are place valued. 1, 2, 3. 1 gets its meaning from the position where it is put. But you see that she has added written, underlined. So for her, this numeration system can be taken into account when it features on paper, but not before. However, if you remember her definition of written numeration, it should be a written numeration that corresponds to an oral numeration. And apparently, these rod numerals were never used to write down an oral numeration. So there is a problem in making a border separating rod numerals written materially with rod numerals written on paper. It's simply a change of writing support. What is striking is that we have exactly the same process in the Arabic world, and hence, most probably, in Sanskrit works from which Arabic writings on the decimal place value notation derived. The so-called Arabic numerals, without entering into details, were first written on dust only, and the works were referring to what was happening on the dust on which one drew numbers. Perhaps they featured as illustrations in early text, it's not very clear. But what is interesting is that from the 10th century onwards, the place value decimal system that was merely material prior to that day migrated onto paper. You see the manuscript here and the translation to the left. Migrated onto paper, but in exactly the same way as the Chinese case that I have analyzed, you see that what is written with Arabic numerals features as figures. It does not feature any place in the text. So, exactly as we had in China, the place value decimal system begins to be represented on paper as figures and hence as separate scriptural spaces. So it's striking that we have at least two numerical systems and a different way of using them, different places on the page or on the surface of writing. What is even more striking is that a phenomenon of exactly the same kind occurs if we observe Mesopotamian tablets, and I will rely on the work of my colleague Christine Proust on the tablets, mathematical tablets that were produced in a scribal school in Nippur at the beginning of the second millennium before the Common Era. So this is a text that she considers was the foundation of the mathematical training. It's a metrological table. To the left, you have quantities, metrological values, measurement values, written with one way of writing numbers. To the right, you have pure numbers that are written in a system which is completely different. This table teaches students to translate each expression of a measurement value into a pure number, and you see that we move from 9 sushi to 1.30. So it's not innocuous in terms of association, it's not obvious. What is even more striking are these exercises that pupils were given, where in fact you have in the bottom right corner the inscription of an exercise, and you see that here you have the expression of measurement values in the text, okay? But separated from it from a spatial viewpoint, on the left top corner, you have the famous pure numbers of the right column of the metrological table. So the left column of the metrological table occurs only in this corner, and the right column occurs only in the top left corner. And what this means is that an exercise is set here with measurement values. The student goes to the metrological, it's a computation of the area of a square. So the student takes the length, translates with a metrological table for length the measurement value into a number that he or she inscribes in the top left corner. When the two values to be multiplied as pure numbers are there, a multiplication table is used, the result is returned, and the result as a pure number is taken to a metrological table for surfaces, transformed into the measurement value for the surface, which is written back into the lower right corner. So here again, you see that there are two scriptural spaces for two types of numerical signs, and hence this striking phenomenon that in many contexts of the ancient world, some actors shaped and used at least two different numeration systems in different spaces. These systems were not interchangeable. Hence, not all systems or not all numerical signs should be considered as having the function of writing down language or expressing quantities. To understand better what is at stake, I suggest that we look at a page in Chinese from a book dealing with mathematics. This is Chinese to us, but here, right in the middle, there are inscriptions that we can read. There are inscriptions that are clearly mathematical that we can understand. These are mathematical formulas that are used worldwide today in any language. They have the same features. They are verbalized differently depending on the language one works with, but they are written in the same way. About these inscriptions, these formulas to begin with, Charles Burnett has this to say. I read, mathematical notation is independent of language. You see that we return to a topic on which I've been insisting. Mathematical notation is independent of language. It is symbolic and does not represent sound. We will return to this. Therefore, there is no need for different notation to be used in different languages, even when they are written in different scripts. Nowadays, the same mathematical notation is used and understood throughout the world by Chinese, Arabic, Russian, and American mathematicians. There was a potential for this to happen in the Middle Ages. So, first thing on which Charles Burnett insists, mathematical notation is independent of language. One might verbalize them, but they are circulating independently of language. Here he's speaking of formulas, different languages, a single notation, widely shared. Now, if we return to the page in Chinese that I have shown a moment ago, we see that it's not only the formulas that we can read. We see that there are numbers written with a place value decimal notation that we can read. I have highlighted them in blue, and in red, I have highlighted the other numerical signs that feature on this page, and that are numerals written with the characters of the Chinese language. So, if mathematical formulas circulated, the place value decimal notation circulated as well. Here is what Burnett writes about the decimal place value notation, the paper I've quoted, is about the circulation of the decimal place value notation. At odds with Gittel's focus on written numeration, he adds the Indians had invented a symbolic notation for the 9 digits and the 0, which was taken over by Syrian Arabic writers and eventually passed to Western Europeans. Scholars writing in Syriac, Arabic, Latin alike refer to these symbols as Indian figures. And they all participated in the same distinctive method of calculating with them. Thus, a common mathematical language was shared by mathematicians in Bath, Baghdad, Roskilde, and Marrakesh, despite the fact, he insists later on in the page, that at the time there was a diversification of signs, but they shared the same system. I would add to this list some Chinese practitioners of mathematics. And hence, like formulas, the place value decimal system circulated. Independently of the language writers were using, they used a similar notation. Sometimes it was an ephemeral notation on dust, on wax, with rods, but they used the same notation. And similarly, these notation migrated. It's difficult to assess exactly when for Sanskrit text, but more or less at the same time, it seems, in China and in the Arabic world. And I would add to what Burnett emphasizes that we have seen that these signs, this place value decimal notation, they did not have the function of expressing numbers or quantities. With respect to the history of mathematical symbolism, there is, since at least the 19th century and probably earlier, a common history. I have taken Edouard Biot, Jean-Baptiste is his father, who was the first European specialist to write about mathematics in China. So his first paper, published in 1835, is about a Chinese book published in 1593, 1592. It's not an issue here. And here is what he writes about this book. Nowhere in this book, nor in those of the Arabs and the Hindus, do we find the notation by letters used symbolically to express numerical quantities as we do today. This invention, which makes the genuine strength of algebra, is wholly European and due to Vieta. In fact, documents from China will help us suggest a different story in line with what Burnett suggested. Why? Because in China, fortunately enough, we have groups of documents produced by different social groups who computed differently. They used different numerical signs and they computed differently. And comparing how they computed sheds light on a feature of the place value decimal notation on which I've not yet dwelled. But note that if in China there were different social groups computing differently, that means that we should not have peoples as chapters in histories of numbers, but rather social groups. And I will not go on with this issue, but it's a very important issue. So let us observe extremely quickly how different social groups computed. I'm not going to dwell on how they computed. I just want to give you some insight, okay? So I'm going to go very quickly. You are not going to be able to understand at the speed at which I will go, but what I would like to give you is a sense of the difference between the way of computing. So I will place myself at the beginning, in first decades, let me say, of the 7th century at court in China. At court, in the first decades of the 7th century, we can observe different social groups computing differently. So that's already pretty striking, and that does not fit with our representation of primary school education making things look uniform for all of us. So the first group, which was recently uncovered by a Chinese colleague of mine, Zhu Yiwen, is a group of people who write sub-commentaries, that is, commentaries on commentaries of classics, and they write sub-commentaries on Confucian classical books. So in these classical books, you have statements stating measurement values about something, and here we have a 2nd century classical commentator saying, no, here it is said that this volume of one shirt side corresponds to this capacity. This is wrong, the commentator says. There is this amount of capacity missing. I don't want to dwell on what this means and so on. What the sub-commentator will do is to develop a computation to account for this difference that is stated by the 2nd century commentator. To do this, he represents the cube of one Che side. Che is a measurement unit of length, but it's also a measurement unit of volume. And here is how it works. So this is the shape that has the volume of one Che side. This is what the text speaks about. And this shape also represents the geometrical shape of the quantity. A volume is said to have one Che if one Che is the height of a cube of one Che side. So if I wanted to express the same volume with a cun which is 10 times smaller, I would cut this cube into parallelepiped, and I would put 100 parallelepiped on top of each other. I would have a parallelepiped of 1 cun side and a height of 1,000 cun. So there is a geometric shape that is associated to the quantity. Then a relation is brought into play that connects volumes and capacity, and the volume corresponding to 10 Do is represented again by the geometric shape of the quantity, and then the author will establish a scale, a right cuboid of a square base of 1 cun side and a height of 16 cun 2 fen corresponds to 1 Shang capacity. The Shang is 1/10 of the Do. He goes on with establishing his scale, a right cuboid with a square base of 1 cun side, the same, and a height 10 times larger corresponds to a capacity 10 times larger than the previous one. And he's going to compute the volume corresponding to the capacity that is stated in the classical text. And for this, he's going to take first 6 Do, and he's going to use his scale to compute how much volume 6 Do corresponds to. So 6 Do, I multiply the volume corresponding to 1 Do, 6 times 100, 6 times 60, 6 times 2 cun, and so on. And I'm not going to get further into the detail of the computation, but what I want to emphasize is that in this text, the authors express quantities, express numbers with Chinese characters. They use no tool, they use no rods, they use no temporary surface, no temporary notation for numbers. But they compute by means of reasoning. Each step they do, they know the meaning of that step, and when they get to the result, they know the meaning of the result they have computed. This is essential because this is different from what we have in a second set of documents that in the 7th century was used in the University of Mathematics to study mathematics. These are the texts expressed numbers in the linguistic part of the text, the discursive part of the text, with Chinese characters, in which one has no computation. However, these texts refer to computation carried out with rod numerals. So I will show you very briefly the division, because what I would like to give you a sense of is that I have replaced rod numerals by Arabic numerals so that you understand a bit what is happening. The computation will draw on the inscription to develop formally without making clear what the meaning of the steps are. So you operate on the inscription, you move numbers, you operate on the inscription until you get the result. So here you have what I refer to as a formal way of dealing with number inscriptions. So, in conclusion, I would like to emphasize that in China we have a diversity of numerical signs, diversity in the nature of the signs, diversity in the use of the signs. Some actors make use of the Chinese characters to compute, others use technologies that are outside language. We have families of uses of the decimal place value notation in China, in South Asia, in the Arabic world, in restricted milieus, not all the milieus, but in restricted milieus across linguistic border. The sharing of numerical notation that they show in their writings took place across border. This is what Charles Burnett emphasized in a way that is similar to what we see with the algebraic symbolism today. So perhaps the history of the algebraic symbolism should be revised. Perhaps we might establish that algebraic symbolism was rooted in the formal work through which computation were carried out on the basis of decimal place value notation. And hence, the history of mathematical symbolism would no longer be merely European, but global. Thank you very much.
People are interested in those words that we have for numbers. Can they tell us something about the way in which calculation is done? So, some of the words for numbers perhaps are telling us about whether we count in tens or 20s, something like that, I guess. Yeah.
Okay, so in fact we have words for numbers and we have words referring to types of numbers. And here we have a character which is swan. So here this character swan means rod, borrow a rod. But this character can be used to refer to those numerical signs that are written with rods, those computations that are carried out with rods. Whereas another term that is quantity, which features in text. Can I see it here? I'm not sure I can see it immediately. The number, the term referring to quantities, probably numbers written with characters, might be different. So we might have a terminology opposing the different kinds of characters. So now I understand that the question was not about the concepts referring to different types of numerical signs, but the numerical signs themselves. So in the same way as when we write 1, 2, 3, the 2 does not express the relation to 1. If you take the character for 5 and the character for 6 or 7, the characters do not express the relationship between the quantities. This does not hold true for the rod numerals, where we have seen that it was in the table here, where we have seen that the signs, the numerical signs writing the numerals, show the relationship between these numerals.
I wanted to say I'm very blown away by your lecture, but my question is primarily referring to the history of those groups. Out of the African continent, I saw you mention Egypt and Ethiopia, and that's very fascinating because we know that in the 18th and 19th century, Europeans actually considered both Egypt and Ethiopians to be Caucasian in their view of anthropology. And perhaps this has to do with the fact that in both countries you had a lot of science and a lot of artifacts, and they couldn't imagine that being done by Africans south of Sahara. So I wanted to know, in your research, what do we actually know about us, even Africa, Austral, Southern Africa, or Sub-Saharan Africa in any mathematics? Thank you.
Thank you. So there is a book by Claudia Zaslavsky, Africa Counts, to which I can refer you. You see, I would say that I'm at the beginning of a new road with respect to the inquiry into the history of numbers. Many histories of numbers were written through a decontextualization of where numerical signs occurred. This table is a very good example because, in fact, it takes signs out of their context, out of their scriptural context, and it gathers all these signs in a table, and it reads a process of evolution. Whereas, in fact, all these signs did not occur in the same parts of the writings. When they occur in coins, it's not a text. So what is exactly this sign? So the research that I have carried out with my colleagues in Paris has led us to the conclusion that one should re-examine the history of numbers by relocating the signs in their context. And in fact, the context of occurrence is not enough. We also need to pay attention to how the actors used these signs, because everybody used the characters of the Chinese language, but differently. Some computed with it, others simply recorded results without computing with Chinese characters. So I know there are people who worked on the history of numerical signs in Africa. Claudia Zaslavsky was a pioneer in this respect. I cannot judge her work, because to judge her work, I would need to have the documents and to observe how the numerical signs were treated. So it's a very modest and poor answer that I'm making to your question. I wish I could tell you more, but I really hope that some people will take up this task and help us understand the diversity of numerical signs that we find in Africa, and the diversity of what I call cultures of computation.
Very simple thought. If I remember it correctly, it seems that the rod system equates exactly to the Chinese abacus.
So, thanks a lot for this question. Again, this slide will be helpful to answer this question. So, as far as we know, the abacus became widespread in the 15th century, the 14th century. It's unclear when exactly it became a computing tool that was used broadly in China. Before then, practitioners of mathematics, practitioners of the astral sciences, some specific groups were using rod numerals in their scientific work. So first of all, in terms of diffusion, these are two different worlds. Not everybody was using rod numerals when some specialist group were using rod numerals. The abacus was infinitely more widespread. I should be more cautious here because we do not have, for instance, we do not have any document produced by merchants from the beginning of the Common Era. So perhaps we would discover that they too used rod numerals. We do not know. But for sure, there were different milieus using different ways of computing. Now, the relationship between rod numerals and the abacus is that in the same way as in the abacus, you have unit rods and on top of the horizontal bar, rods for 5. In the rod numerals, you have unit rods and a rod for 5. You know that there are various kinds of abacus, some with 1 rod on top of the horizontal rod, some with 2 rods, some with 4 beads, 4 beads under the horizontal stick, some with 5 beads. There seems to be a lot of continuity, so there seems to have been a transfer of ways of computing with rods into ways of computing with abacus. However, as early as the 16th century, we see different ways of using the abacus in China. So one of my former PhD students has established that there was not a single way of using the abacus, and the 2 rods, the 2 beads, on top, the 2 times 5 on top, could be used differently in the computation. Incidentally, this is extremely interesting because, again, with the abacus, we see the difference between expressing numbers and computing with numbers. If with the abacus we only express numbers, we would not need 2 beads for 5 on top of the horizontal stick. So the abacus is not made to express numbers, it's made to compute. So here we have a very clear instance of numerical signs, material signs, that are made for computation and not for the expression of quantities. But there is a continuity in the practices of computation from rod to the abacus.
I'd like to thank all the organisers that have put together this set of talks today, and to the speakers, and especially to Karine Chelma for that fantastic keynote speech.
Thank you so much
Thank
for
you.
Everything.